Well, hello. So I couldn't quite hear back there, so I wasn't sure when I was supposed to come out, but anyway. Yeah, this field of network protocols is incredibly confusing. And, why are there so many different protocols? What's the difference between a new protocol and a new version of an existing protocol? What's the difference between a layer 2 solution and a layer 3 solution? And I'll try to illuminate some of that, as well as sort of tell you the history of some of the stuff, which is hysterically funny, and without knowing it, there's no way to understand how things are today. So my general philosophy about protocol designs, because I actually am totally intimidated by technology and gadgets and stuff like that, and I think we need more people in the field that hate computers. So I always believed in building things that completely configure themselves. You don't even have to understand what's going on. It just works. And then, after a few years of that, people told me, Radia, there are some customers that really want to have knobs to diddle and really feel like they're controlling things. So now I make it so that you don't have to touch anything, but if you want knobs, I'll give you knobs, and any setting of the knobs will still work. And another sort of, philosophy is don't say, oh, let's design everything from scratch. I mean, sometimes you can do so much better that it's worth it, but usually you don't really need to. There's not that much about a network protocol. So figure out a way that whatever's out there, add functionality in certain boxes, and you don't have to throw the rest of it away. And that kind of philosophy is how Trill, which we'll get to, works. So a lot of what everybody knows about network protocols is actually false. So how networking tends to be taught, which really frustrates me, is as if it's like TCP/IP arrived on tablets from the sky in its awesome perfection. Nothing else ever existed. And they say, hey, memorize these RFCs. And if you mention any other standards body like ISO, it's only to giggle at what morons they were or something. My philosophy on teaching and on books is that you look at a particular conceptual problem, like, hey, you plug into a network, how do you get an address? And I say, well, here's 7 different ways that I can think of, here are the trade-offs between them, and then I'll say, and by the way, IPv4 does it this way, IPv6 does it this way, AppleTalk did it this way, IPX, DECnet, etc. But some professors say, why is this stuff in there that students don't need to know? As if students have like a very, very small brain, and if you fill it with any facts that a recruiter is not going to ask on a checklist, it's sort of, right, wasting space. But so I will continue doing it that way. I mean, there's a lot of professors that do like the way that it is, but I wish more things would be taught that way. So one of the things I like to try to puzzle out is when there's 2 competing things, technology A versus B, I want to get to the heart of what's really different about them, what's better about one versus another, but no one else seems to know both of them. And so I'm presented with 2 600-page specs, all in their own sort of incomprehensible jargon, and to try to puzzle out what's better about one versus another, I might try to save myself time by asking a specialist in technology A, how does it compare with B? And they say, well, A is awesome and B sucks. And of course you get the opposite answer from the... So then if you discover things that are better about B, and you tell the A people, actually it works better in these cases, and it's more scalable, no problem. They steal the ideas, and so you have 2 moving targets, So what about facts? What if you actually measure A versus B? So that sounds really scientific. But the problem is, what are you actually measuring? You're measuring one implementation of A versus one implementation of B. And so one example, someone was trying to show how technology A was so wonderful compared to B, and they said A has 4 gig of throughput, B has 1 gig, and throughput's an important thing. But I have this sort of checksum that I require, which is I need to understand something intrinsic about A versus B that would make one have 4 times the throughput. And I couldn't for the life of me figure out what it could be in this case. So then I asked, were you using a 1 gig physical link when you were measuring B? And they said, yeah, that's all I could find in the lab. So don't believe anything unless you can, even if it's measured or something, even if it's on a PowerPoint slide, it doesn't make it true. So now I'll tell the story of Ethernet. So what exactly is Ethernet? You probably all think it's a successful technology, but actually it died out decades ago, the thing that was actually invented. And so I'll sort of tell the story. So people talk about layer 2 solutions and layer 3 solution. That's sort of a completely nonsensical thing, as we'll see. So first we need to review network layers. So ISO was a standards body, international standards body, that was credited with naming the layers of networking. And it's just a way of thinking about networks. Nobody says you have to have these layers. Most of the layers are broken up, so, whatever. But it's just a good way to start thinking about it and have separate committees, because the kinds of people that can design connectors are not the same people that would design syntax for applications. So this is my view of the ISO layers. The first layer is the physical layer, which sort of says how do you signal a bit and what does a connector look like. The hardware people do that. Data link is how you get a message to a neighbor. So all it's doing is I can already signal bits, 1s and 0s, because of the physical layer, and somehow I have to signal this is the beginning of a packet, here's the data, here's a checksum, here's the end of the packet. So that's layer 2. Layer 3 is the thing that creates an entire path and forwards the packet. And an example of that is IP. Layer 4 is end-to-end stuff like TCP, which might put packets back in order, retransmit things that were lost. And layers 5 and above are boring. So that's why I say it's mine. ISO didn't describe it that way. So why are we forwarding Ethernet packets? Ethernet was intended to be a layer 2 thing, which was just between neighbors. So but we do forward Ethernet. What's that about? So what exactly is Ethernet? So, as I said, there's no way to understand it without seeing the history. So back then, before Ethernet, I was the one designing layer 3 of DECnet, which means that, I did routing protocols and stuff like that. And by the way, the routing protocol that I did in the 1980s is still in use in most ISPs, I've heard. ISO renamed it ISIS, stands for Intermediate System to Intermediate System. Anyway, and I'm actually way more proud of that than the spanning tree, but oh well. So layer 3 is the thing that does a distributed algorithm to figure out forwarding tables in the switches so that they know how to move the packets around. And layer 2 just marked the beginning and ends of packets. Then along, as I said, came Ethernet. So Ethernet was a new type of link, and I said, oh my goodness, it's a new type of link. And I was used to point-to-point links between 2 computers. Here's something that you have like 100 computers all interconnected. So, there were little things that I had to do to the routing protocol to accommodate this new kind of link. And an example of that was inventing the concept of pseudonodes, where if you have a link on the left here, can you see little arrows if I do that? Yep, this thing, since the routing protocol, the storage is, the complexity of it is the number of links, this thing would take a lot more, would be less scalable than adding an extra node called a pseudonode and having everybody just connect to that. So just little things like that. So I wish they'd called Ethernet an Etherlink, but because it was so bright and shiny and hyped, everybody got all confused. So the original invention was just a way of cheaply hooking together lots of nodes on a single link. Everybody could directly talk to everyone else, and there was no forwarding of data packets. So the original thing was CSMA CD, which I notice I have like ingrained in my brain. So at meetings, you know, I just can't interrupt somebody. It seems like most other people don't think of it this way. But CS is be polite, don't interrupt. Carry your sense means listen to see if someone else is talking. Multiple access means you're sharing the air, don't just sort of talk the whole time. And CD is listen even while you're talking in case somebody interrupts you. There's lots of perfectly valid academic papers about how under load you can only get like 60% of useful throughput because of all the collisions, and it's limited in terms of the number of nodes, like maybe 1,000. But even though those are perfectly valid papers, I see people still sort of confused today that it has something to do with Ethernet, but it has nothing to do with today's Ethernet because we don't do CSMA CD. It hasn't been that way for years. So what exactly is it? Well, an Ethernet packet, you put your data in an envelope and you say the destination and the source. A layer 3 packet is very similar. There's the destination and source, and there's this hop count. Now, the reason for the hop count is that in a distributed algorithm, it's hard to have everybody instantaneously switch to new forwarding tables if the topology changes. So you might have packets circulating because they're kind of lost, and it would be good to put them out of their misery and not waste bandwidth after they've gone around a while. So I think it's actually irresponsible to forward packets without having a hop count in the header. It's easy to confuse Ethernet with a layer 3 protocol. It looks kind of the same. There's no hop count field. In Ethernet, addresses are flat, meaning there's no way to summarize a bunch of addresses with one forwarding table entry. So Ethernet would not be suitable for replacing the Internet. But the Ethernet inventors never put in something like a hop count because it never occurred to them anybody would be forwarding these packets. So why are we forwarding these? So people got confused and they built applications directly on layer 2. They thought Ethernet was instead of layer 3. It was the new kind of network. So I tried to argue with them. You know, there was a group at Digital doing something, and I went over when I found out they were going to leave out layer 3, and I said, no, you still need layer 3. And they said, oh, go away, you're just upset because your layer is a dinosaur and we don't need it anymore. And I said, but you may want to talk from one Ethernet to another. And they said, our customers would never want to do that. So indeed, they made a wonderful protocol and made lots of money, so they were big heroes. They would have made just as much money if they'd done it the right way on top of layer 3. So, I mean, a router, an ordinary router, I've been told not to call them routers here, by the way. A router can't forward unless you put it in the right kind of envelope. So one day, when I was kind of in a bad mood about this whole thing, my manager says to me, Radia, we need to design a magic box that will sit between 2 Ethernets and let somebody on one talk to somebody on the other, which of course is a router, but it only works if the end nodes have been designed with layer 3. So the constraint was it had to be done without modifying the end node or the Ethernet packet in any way. So we couldn't add to the length of the Ethernet packet, we couldn't change a single bit, and we had to work with however end nodes would work just on a single link. So the basic concept was that this magic box called a bridge listens promiscuously, meaning it listens to every single packet on each port, and when the ether is free or whatever, it forwards it onto the other ports. It also can learn based on the source address where somebody is, so that in the future, if there's a packet addressed to someone he's heard from recently, he doesn't need to flood it through everything. He may not need to forward it at all if it's on the same port that he heard it from. This basic idea requires a tree, a topology with no loops. So this is the basic concept where this guy has learned that A is on this port. And so if J transmits a packet with destination A, it doesn't need to forward it. If A transmits a packet for destination J, since it doesn't know where it is, it has to forward it on both ports. So the spanning tree algorithm, basically you just plug it together, and the bridges with no configuration necessary, but there are some knobs if you like to play with knobs. With no configuration necessary, they gossip amongst themselves and figure out a loop-free subset of the topology. So here, hopefully you can see, they've turned off some of the ports, so there's only one way to get from any place to any other place. So the story of it was kind of cool. My manager asked me he said, you do distributed algorithms, do this thing. And he thought it was going to be really hard. And so he also decided he was being witty, and he said, oh, just to make it even more of a challenge, make it scale as a constant. So the amount of memory necessary to run it should be a constant no matter how many links and bridges there are. Now that's absurd. Nothing is a constant. You know, linear maybe, probably n squared. So he was going to be gone the whole rest of the whole next week, and this was before, you know, cell phones or email or electricity. So that night, that Friday night, I realized, oh my goodness, it's trivial, and furthermore, it scales as a constant, because if you're a bridge and you have 5 ports, you have to remember the best spanning tree message you've seen on each port. When you're reading packets in, you see, is it a spanning tree message? If so, is the one that I just received better or worse than the one I have stored? And so that's a very easy check. And the size of the message is about 50 bytes. So if you have 5 ports, it takes 250 bytes to run the algorithm. So it's such a trivial algorithm, it was, you know, obvious to me that it worked. And then Monday and Tuesday I spent writing the spec, and I did it in enough detail that the implementers got it working in just a couple of months without asking me a single question. And then the remainder of the week, I couldn't concentrate on anything else because I had to show off to my manager who wasn't around. So the remainder of the week, I worked on the poem that goes along with the algorithm. And it's actually the abstract of the paper in which I published it. So it's called algorhyme, because every algorithm should have an algorhyme. I think that I shall never see a graph more lovely than a tree whose crucial property is loop-free connectivity, a tree which must be sure to span so packets can reach every LAN. First, the root must be selected. By ID, it is elected. Least cost paths from root are traced. In the tree, these paths are placed. A mesh is made by folks like me, then bridges find a spanning tree. So then it was sort of cool. I mean, I thought it was a really bad thing to do. I actually was saying, no, make them put layer 3 back. I was nervous about forwarding without a hop count and stuff. But, you know, still, and I didn't want to argue that, the implementers were saying, well, we don't want to complicate our basic idea of just moving packets around with this spanning tree algorithm. Even as trivial as it was, it made their product more complicated. So I stayed out of the argument, but upper level management decided that they had to put it in. You know, they just wanted to tell the customer, don't put in loops. But then we sold the very first bridge, and we sold it to the world's most sophisticated customer at that point in history. And they had the world's simplest topology, which was 2 Ethernets, 1 bridge. And I heard after the fact that the sales guy was saying, oh, do this thing, and they were saying, oh, but we're doing all this complicated networking stuff. And the sales guy was saying, oh, it's just going to work. And they said, we want to talk to an engineer. And the salesman said, no, you don't need to, it'll just work. So the world's most sophisticated customer with the world's simplest topology plugged it together, and it didn't work, and they were very unhappy. But when the field service people went to find out what had happened, they discovered this. So, it was working perfectly. Spanning tree algorithm said, I don't seem to need to forward packets, so I won't, but if I ever do, I will. So if they could get that topology wrong, it was right to make them do it. So the problem with spanning tree is that your paths are not optimal. If you look at A transmitting a packet to X, it has to go this really long way through 11, 7, 6, 2, 14, 4, 3, and X. And you might think, well, that was a silly spanning tree algorithm. If it were a smarter algorithm, you could have come up with better paths. And no, that's not the problem. If you have one shared loop-free thing, some people will be unhappy. If you imagine the topology being a big circle, you have to chop it someplace, in which case people on either side of the chop have to go around the long way. There's sort of no way to avoid that. And traffic gets concentrated on the links that are used in the tree, and other ones don't get used at all. So why not just replace bridges with IP routers? These days, everybody has IP in their network stacks. So, and even back then, there were lots of different layer 3 protocols. Now everyone speaks IP. So why not just replace the bridges? Why are we still doing this spanning tree stuff? And the reason, which is something you will never get from one of these books that just tell you, TCP/IP is the only way to do things, is that IP is actually not a very good layer 3 protocol. And arguably, of all the contenders, it was sort of the worst. It's sort of like English may take over the world, but it's not because English is the best language. You could look at Dutch or something and say, clearly they have too many consonants, but there's nothing, it wasn't technology that caused IP. So what's wrong with IP as a replacement? The problem is IP is configuration intensive because every link in IP has to have its own address block. So if you want to number your enterprise with IP, you have to chop up your address space. You have to configure the routers with what addresses are on which ports. And if you have a node that moves from one place to another, it has to change its layer 3 address. So layer 3 does not have to work that way. So when I was in charge of layer 3 DickNet, we had a 2-byte address. And then we were saying, 2 bytes might not be big enough, let's increase it. And then we said, hey, we don't have to invent our own format. ISO has a perfectly reasonable envelope with 20-byte addresses. So we adopted ISO's packet format. The address, that was called CLNP, the ISO thing. It was a 20-byte address where the top 14 bytes you could think of as a prefix for your entire cloud or your entire enterprise. And then the bottom 6 bytes, you put your Ethernet address in there. So the way a router would work is if the top 14 bytes were the same as the cloud, then it routes based on the bottom 6 bytes, keeps track of where all the end nodes are, and the end nodes help out by announcing, hey, I'm over here. So if you have one prefix per link, like IP, you have a lot of configuration, and if you move around, you have to change your address. If you have one prefix for the whole campus, then there's no configuration of the guys inside. Someone has to be told the 14-byte prefix, but that's it. And you could move around within that and keep your address. So the single worst decision in the history of mankind was that in 1992, someone said, hey, IP addresses are too small. Why don't we adopt ISO's packet format with 20-byte addresses? But just because of, sort of this not invented here. Oh yeah, right, something I should say. It's natural to think of standards bodies as sort of well-educated technologists carefully considering engineering trade-offs, but a much more accurate way of thinking of it is as drunken sports fans. So when somebody proposed replacing IP with CLNP, people were saying, no, we don't want to give ISO the satisfaction of saying anything they ever did was okay. They were saying, are you talking about ripping the heart out of the internet and putting in this foreign substance or whatever? So they decided they would go in. Oh, and imagine if we had done that in '92. The internet was just this researchy thing. It would have been trivial to move it to bigger addresses back then. And furthermore, IPv4 had not invented things like DHCP and NAT. So CLNP, it was if someone said, why should I do this? You'd say, you get auto configuration. And they go, oh yes, sign me right up. But we've kind of out of necessity made IPv4 more and more easy to live with. And the longer we live with it, the harder it's going to be to convert the internet. It's right. And at least you think, well, okay, so they had an extra 20 years to design IPv6. It must be awesomely better than CLNP. But all it is, okay, so it's 16 bytes instead of 20 bytes. But CLNP still has some advantages over IPv6 because people tend not to try to even learn from other things because that would just be a waste of their time. They're way smarter than anyone else ever was, right? So IPv6 still has the property that every link has its own block of addresses, so if you move around, you'd still have to change your address. So therefore, people are still going to want Ethernet to create a nice flat cloud that you can move around in for virtualization. So Ethernet looks like a single link to IP, and so we want to get the best of both worlds. Given that we're not going to displace IP, or even if we displace it with IPv6, we'll still have the same problem. So we want to be able to create a large flat Ethernet, but we don't want to have the limitations of spanning tree. We want to be able to use multiple paths. We want to use shortest paths. We want to do traffic engineering, all of the things they've been doing in Layer 3. So this is where, actually, I proposed this thing that became a working group in IETF, and the initial thing has been standardized. It's called TRIL, because it stands for Transparent Interconnection of Lots of Links, which will hopefully sort of give you the best of both worlds. So the TRIL switches form a network between themselves. So they run a routing protocol, and actually a link state routing protocol, happens to be ISIS, where if you have a cloud of spanning tree, you can replace any subset of your bridges with TRIL switches, and the more you replace, the better bandwidth you get. You don't have to throw everything away. And so the TRIL switches know how to reach other TRIL switches, and then you put your Ethernet packet into a TRIL header, which is like a Layer 3 header that says who the first switch is and who the last switch is. So A transmits an Ethernet packet, R1 puts it in a TRIL header, addressing it to R2. The guys in between here don't need to know anything about where the end nodes are. They're just routing towards R2. R2 removes the header, and out pops an Ethernet packet again. So this is what a TRIL packet looks like. It's a 6-byte header. The switch addresses are 16 bits, which are auto-configured, so you don't have to configure them. They're just sort of part of the routing protocol. People manage to get a unique 16-bit address. And so there's first switch, last switch, and a hop count, and the original Ethernet packet. So 16-bit TRIL nicknames, it does allow 64,000 switches, and it allows many more end nodes than that. Is that scalable enough? I don't know. The nice thing about a small address like that is that your forwarding table lookup can be very simple. You don't have to do hash or longest prefix match or anything. You can do 64,000 entries. You just do a direct lookup into that table. So the advantage of this extra header is that the switches inside the cloud don't need to know about all the end nodes. Only the guy at the edge needs to put on the header. And so their forwarding table is the size of the number of switches rather than number of end nodes. And the outer header is like a layer 3 header, and you can use all of the standard techniques. Plus it has a hop count, my favorite field. So how does R1 know that R2 is the correct last switch? That's really orthogonal to the rest of Trill. There's various possibilities. The initial versions of Trill kind of work like bridges, where when you decapsulate a packet, when you're R2, you look to see the source MAC address in the inner Ethernet header and the first switch in the Trill header, and you remember, if you want to send something to that MAC address, you should send it to the guy who you received it from. Or you could configure the edge switches if you, want to lock everything down, or there could be a directory that when R1 doesn't know where the destination is, it queries the directory. And, or you could have a central fabric manager that pushes the table to the switches. Another little thing is, for some reason, people wanted to multipath everything, including multicast. So as part of the link state routing protocol, there's enough information to calculate one or more trees. So the idea is you calculate several trees, and if you look at the Trill header, last switch doesn't make any sense on a multi-destination frame. It does for unicast, but not in multi-destination. So for multicast, the campus calculates some number of trees, let's say red, yellow, and blue, and when R1 injects it, R1 specifies in this field which tree it should be transmitted on. And link state routing, just to demystify is that here's a network of 7 nodes. F and C are neighbors with a link cost of 2. Each one of these guys has, generates a packet saying, I am A, I have a neighbor B at a cost of 6, D at a cost of 2. That gets forwarded to everybody, and then they know everything about the network. They could calculate paths from themselves to everybody. They can also calculate trees. And they also can get a unique nickname for themselves by just putting into their link state packet, which is going to get flooded to everybody, I want to be 42. And if nobody else has chosen that, you get to be 42, and if not, if somebody else has it, whoever has the smallest or largest 6-byte unique address gets to keep that nickname, and the other one chooses a different nickname. So it's evolutionary, as I say. You don't have to throw everything away. The more switches you upgrade to Trill, the better bandwidth and the more stable it gets. There's also another little thing about spanning tree, which is that if you can't keep up with wire speed, then you will falsely start bringing links up. And if you couldn't keep up with the amount of traffic you were getting before, just because of normal traffic spikes, if you then start falsely bringing extra links up so there's looping packets and no hop count, the entire network melts down, and this actually happens. So it was actually after one of those things that made the news that I decided it was time to apologize to the industry for spanning tree and do this other thing. Another orthogonal concept is who is it that puts the Trill header on? It could be the first switch, or it could be the hypervisor, or the virtual machine, or even the application. For making it sort of most painless, it's sort of nice to do it in the switches, but pushing it closer to the application is nice because that way the switch doesn't have to keep track of all the destinations that a particular application is talking to. It can take the responsibility itself, and furthermore, it knows if it's not working, so it can immediately, if the entry is not working, it can relearn it by asking the directory or flooding the packet. So, oh yes, so my son was very familiar with the algorithm poem because my daughter is a musician. She's a violinist and she's an opera singer, and I've always been her piano accompanist. So one time she was doing a recital and singing opera, and so all these Italian and German arias, and my son decided it would be fun. I mean, they're both grown up, they're not like 3 and 6 or something. They're grown up. So my son thought it would be really cool to set the algorithm to music, and that was one of the arias that she performed. So it's actually on the internet. It wasn't the best performance of it for various reasons, so I wish we could have done it again if I'd known someone was going to actually record it. But at any rate, when I was giving kind of the first talk about trill someplace, I was realizing, hey, there's not enough jokes here. So I called up my son at 10 o'clock at night, and I had to fly out the next morning, and I said, hey, here's how this new thing works. Can you come up with a version of the poem that describes this new thing? And you have 1 hour, because I want to go to sleep. If you've done a good enough job, I'll use it in the talk, and if not, hey, you've wasted 1 hour of your life, which you owe me that much. So I called him back in an hour, and he did such a good job that it's actually in the spec. And And I should just tell you one piece of terminology, which is I originally called the thing R bridges for routing bridges, and I've regretted it because every time I try to explain it, people think I'm saying our bridges instead of our bridges. So, but that's in the poem. So I actually suggested in the working group that we replace every mention of R bridges with trill switches, and they said, no, then the poem doesn't work. So, whatever. So algorithm V2. I hope that we shall one day see a graph more lovely than a tree. A graph to boost efficiency while still configuration free. A network where our bridges can route packets to their target LAN. The paths they find to our elation are least cost paths to destination. With packet hop counts, we now see the network need not be loop free. Our bridges work transparently without a common spanning tree. So recently there's been a bunch of similar things invented. If you haven't heard these acronyms, congratulations, I wish. But, NVGRE and VXLAN, what are these things? They're basically the same thing, that you have a flat address space and you put an outer header that says where you are. So, for instance, inside with Trill, the yellow thing, the flat address space is Ethernet. And some of these other things have IP as the inner thing. And it's just, you treat IP as if it's a flat address. To me, I think Ethernet, you could do either one works. I think Ethernet is better because it gives you bigger addresses with a smaller header. There's a whole bunch of junk in the IP header that you don't need for this purpose. And everyone knows how to get globally unique Ethernet addresses to auto-configure, and with IP it's going to be more painful to get a 4-byte address. And the outer header, which, and this sort of is, right. The outer header in Trill is 6 bytes with this nice auto-configured 2-byte address of the switches, whereas with these other things, it's an IP header plus a UDP header or a GRE header and other stuff. So it's like really big, and it's a forwarding table based on 4-byte addresses is not as easy to construct. So I tried to tell this to somebody who was an advocate of one or the other of those, and I was saying, but really it's just like Trill, and they said, no, Trill is encapsulation, and this is tunneling, or vice versa. The two words mean the same to me, but so an interesting geeky note to me, I was trying to think about CLNP, which has the 14-byte address of the cloud plus your 6-byte end node address, compared to IP versus trill, the advantage of CLNP is that you don't need to do this ARP thing in order to find the 6-byte address, because it's carried in the layer 3 address. The advantage of trill is once you get to the cloud, your forwarding table is much smaller because you don't have to worry about where all the end nodes are. Okay, so now, oh goody, I'm doing great on time. So now, sort of lighter stuff, which is things about designing protocols that are so obvious that it's insulting to you that I'm even mentioning it, but everyone gets it wrong, mysteriously. So, one thing is a version number. So, like, notice this packet format, it's IPv4. You'll notice there's a version number field, and the spec says put a 4 there because it's IPv4. What's the purpose of the version number? Is it decorative? Why are we doing that? And so first we have to ask a philosophical question, which is, what is a new version of a protocol versus a new protocol? So for instance, is IPv6 just a mild new version of IP, whereas CLNP would have ripping the heart out of the internet and putting in a foreign substance? You know, in what sense are they any different? Is one so different that it's a new protocol and the other one's just a new version? Well, the only thing that I think that I've ever seen that makes sense with a version number is that an envelope says how to parse the packet. It says what protocol is inside. So in the Ethernet header, there's an ether type that says what's inside, whether it's AppleTalk or IP or, you know, whatever. In IP, there's a field that says protocol type, that says whether it's TCP, UDP, or something else. In TCP or UDP, there's a port that, you know, sort of well-known ports that say what something is. So, I believe that if you want to differentiate based on protocol type, if you give it a new ether type, it's a new protocol. Whereas if you want two different things, as incompatible as you want, to share the same ether type, then, and you want to decide which one is which based on version number, then the second one is a new version of the first. But the only way that can work is if not only do you put a 4 in the field, but you look at it when you receive a packet and say, hey, if it's not a 4, maybe they did something incompatible when they changed the version number. So the IPv4 spec and all the IPv4 implementations don't do that. They just say, write a 4 into this field. So people discovered that when you tried to send an IPv6 packet to an IPv4 node, it did who knows what. It's decided that right here should be the destination address, right here should be the hop count, and it just happily, you know, misparsed the thing. And so IPv6 is not a new version of IPv4. It is a new protocol. It needs to have a different protocol type. And you'd think that they had learned the lesson, and you would think that in the IPv6 spec it would say put a 6 here and look at it, and if it's not a 6, drop the packet, but they don't. They just say write a 6 here. So the other thing is that so you have to say, look at the version number field, and if it's not your version, throw it away. You can do anything you want. You can make it as incompatible as you want, but the one field that you have to leave in the same place is the version number field. So SSL version 2 to SSL version 3, they completely redid the packet format, including moving the version number field. So anyway, parameters. It's good to sort of minimize the number of parameters because customers have to understand them, read documentation and stuff. If possible, you know, just sort of set a number that works well enough. Often a standards body can't decide on a number, so they say, well, we'll leave it as a parameter. No, don't do that. If you can't figure it out, why should the customer? And if possible, make things auto-configuring. But sometimes you have to set a parameter, and you have to make sure that they can't be set incompatibly. So an example of this is a protocol that I was never able to fully explain to my otherwise bright college-age son, which is that there is no such thing as a reliable "I am dead now" message, so you have to periodically call your mother. And there's a possibility of a parameter mismatch, which is how often you call versus how long she waits before calling the police. So, so something I did in ISIS that I didn't think was worth patenting or even writing down, it was so obvious, that in the hello message between neighbors, I say, "Hello, I'm Radia. If you haven't heard from me for 90 seconds, assume we can't talk to each other." And then I send hellos like 3 times as fast as that. OSPF kind of copied ISIS. There was like a big deal, like when they were saying, "Oh, we want a protocol like that," people were saying, "Why not that?" And they were saying, "Oh, we want to design our own thing." Fine. So they kind of copied it, but they didn't quite understand the purpose of that field. So in OSPF, you say, "Hi, I'm Radia. I send hellos every 30 seconds." And what you do with it is you look at the message you just received and say, "What is my hello timer?" "Oh my goodness, my hello timer is 25 seconds. I refuse to talk to her." Which makes the network like really brittle, and why shouldn't you have different trade-off between overhead and responsiveness? But, oh well. Latency. Sometimes you really care how fast it takes to move a packet through the network. So if you care about that, you do what's called cut-through, which is as soon as you can make a forwarding decision, before you've finished receiving the packet, you can start forwarding it out the output port, as opposed to store and forward, where you receive the whole thing first and then you forward it. Now, if you want to do cut-through, what field do you need to look at in order to make the forwarding decision? The destination address. Now let's look at the IPv4 header. There was undoubtedly some sort of meeting when people were putting on the board all sorts of fields they thought might be there, and someone said, "Hey, wouldn't a destination address be good?" And someone said, "Oh, good idea. We'll add that to the bottom of the list." And then there's IPv6. And TCP has a checksum in the header, so if you're transmitting data, you can't start forwarding it until you see the whole data, compute the checksum, and put it in the front. So now, just really quickly, I just see everything as protocols. I'm sort of always observing how people are interacting and stuff. So I'll just, this is just to reward you for having sat through the rest of the talk. So we need standards. When I'm at a meeting, I'm really amused at how some people, wait till the end of a sentence to interrupt. Other people raise their hands. Other people just talk. And you don't get fair bandwidth allocation when people have different strategies. When there's a single transmitter and multiple receivers, realize that when you're talking and there's multiple receivers, not only are there more of them than you, but it also seems to take more work to parse what somebody's saying than to talk. So, therefore, it's worth forming your thought before you acquire the channel. And I notice a lot of other people, though, seem to think that maybe if I ramble enough, I'll happen to say something coherent. Or if I'm sufficiently incoherent, people can imagine I said something profound. So how to keep the channel. Never finish a sentence. And if someone is trying to interrupt you, speak louder. Dating protocol. The less shy person should initiate. But how do you know which you are? We really ought to have numbers that we carry around. Bandwidth is finite, so if there's n parties, be at least conscious of if you're using more than 2/n of the bandwidth. Protocols that don't work. we'll call you if there is a problem, or we'll call you if we want to hire you. So if you don't get a call, did they lose your number? Is your phone not working? You know, they really need to call you in either case. We have this conferencing system where you hit *6 for mute and unmute, and when you hit *6, it goes mute. And I thought I wasn't listening carefully enough, but someone said, yes, indeed, they have the same sound for both, and it's vague enough so that, you know, you could imagine it either says unmute or mute. And then one time I was in a hotel and they put under the door, tomorrow at 2 p.m. there will be a fire drill. Ignore all sounds and behavior of the staff at that time. So I'm almost done. So another hint for good protocol design, you should know what problem you're trying to solve. So I've never done anything complicated. You know, I just sort of like think about the problem from different angles, and then the answer turns out to be so obvious that once I say what it is, you say, oh, any 11-year-old could do that. Other people just dive right in, looking at various special cases, you know, try to work on those, and turns out it doesn't solve all of them, so you keep adding words, and they come up with some marvelously complicated thing everyone admires. Perhaps intelligent design is better than evolution. But the last chapter of Interconnections, I have protocol design folklore, and I have these little boxes I call real-world protocols. So like to illustrate the n-squared problem, I talk about the handshaking protocol, or the wine glass clicking protocol, which kind of doesn't scale. But the one anecdote in it that everyone remembers most, and it's absolutely true, and it will forever cement in your mind why you should know what problem you're solving before you try to solve it, is that when my son was 3, he ran up to me crying, holding up his hand, saying, "My hand, my hand." So I kissed it a few times. "What's the matter, honey? Did you hurt it?" And he said, "No, I got pee on it." So, thank you, that's it. They're a great crowd. Can I take them all home?